Welcome to the lecture covering 3.7 inverse functions. It's 7 a.m. and I am the only person in the room this morning, so I will try to not go too fast through this material since there's not a student in here to ask questions. We'll go ahead and get looking at this material. Okay, so the first thing that you encounter in this section is just the idea of what it means to be an inverse function. So they give us an example from your textbook of a reversible heat pump, and it says, a reversible heat pump is a climate control system that is in an air conditioner and a heater in a single device. Operated in one direction, it pumps heat out of the house to provide cooling, but in reverse, it pumps heat into the building from outside, even in cool weather, to provide heating. As a heater, a heat pump is several times more efficient than conventional. Okay, so that doesn't really matter. So the idea is we have this function of this heat pump where when you're going into the house, it's doing one thing to provide heat inside, and when you're going out of the house, it undoes what it did to begin with of bringing heat in. It undoes it and pushes it out, and we can kind of think of that as how functions and their inverse functions act. So the next little blurb says, if some physical machines can run in two directions, we may ask whether some of the function machines we have been studying can also run backwards. The figure below provides a visual representation of this question. Let me point out here that these are not the same two pictures. If you take a close look, we have X going into the machine here to provide Y, and the machine is function F, and then right next to that we have, okay, so Y, which is the range from function F going into the machine. We're not sure what that machine is yet, but that's what this section is about. And we get out X, and notice X is what you plugged in the first time, so it's the domain of F. So it basically reverses the domain and range. And so if you look at that general note out to the right-hand side, it says for any one-to-one function, f of x equals y, a function, okay, that says f, and it looks like it's raised to the negative first power. That is not a power. That is a notation of the inverse function. So the inverse function of f, note here, you plug the y values in from your original function and you get out the x values from your original function. So what happens when we compose these functions is we just get x. And you can compose them either way. So you can either compose f with f inverse or f inverse with f, and you're going to get x no matter which way you compose them if they are truly inverse functions of each other. So the next note they have is to note that this f with a superscript of -1 is read f inverse. It is not f raised to the negative first power. So we say f inverse of x. And keep in mind, f inverse of x is absolutely not equal to the multiplicative inverse of f, or 1 over f of x. Your inverses are going to be different for different functions, and we'll see how to figure that out. So since we can compose both ways and get x anytime we're dealing with a function and its inverse function, that's how you test to see whether or not two functions are inverses of each other. So what you have to do is you compose the functions both ways, and only if you end up with x composing both ways, only if, then you can determine that yes, they are inverses of each other. If you don't get x when you compose both ways 2 different times, then they are not inverses of each other. So let's take a look. Okay, so I copied over these rules so that you'd have them on the same page. And let's see what we're given here. So we're first of all given f of x equals 1 over x plus 2. And they are asking us if g of x equals 1 over x minus 2, what the question is g equal to f inverse? Well, we have to compose both ways to figure this out. So I'm going to color code this for us. We'll use blue for f of x, and I'll use magenta for g of x. Okay, so the first composition that we want to give a try is f of g of x, or f composed with g of x. So our f is our shell function in this case, which is 1 over something plus 2. And the something that I'm going to plug in is g, which is 1 over x minus 2. So I will point out that there's an understood 1 that gets distributed, so those parentheses just drop off. So I have 1 over x minus 2 plus 2. Well, minus 2 plus 2, those are opposites, so those just make 0. At this point, I have 1 over x. And I never divide fractions. I multiply by the reciprocal, so that's the same thing as 1 over understood 1 multiplied by the reciprocal, x over 1. I multiply fractions straight across. That gives me x over 1, which is just x. I cannot call these inverses yet. I have to compose them the opposite way and see if I end up with just x as well. Then I can call them inverses if that's the case. Okay, so now my g function is my shell function, which is 1 over something minus 2, and the something that is over is 1 over x plus 2. Okay, so I have 2 fractions that I'm trying to subtract here. And here's the other fraction, 2 over 1. I'm going to take care of that compound fraction first. I never divide fractions. I multiply by the reciprocal, so this is the same thing as 1 times the reciprocal, x plus 2 over 1, and then that's minus 2. Well, 1 times x plus 2 over 1 is just x plus 2, and then I have minus 2. X plus 2 minus 2 is just x. Okay, so since I got x here and I got x here, these are inverses of each other. So with the question, does g equal f inverse? The answer is yes. These are inverses of each other. And I could rename the g function f inverse of x, since I now know that they are actually inverses of each other. All right, let's give this next one a try. So we'll start out with the f function, f of x equal to x cubed. And then I also have g of x equal to the cube root, x cubed minus 4, and g of x cube root of x plus 4. Okay, so we need to compose both ways. F of g of x equals something cubed minus 4, and that something is g of x, which is the cube root of x plus 4. Well, anytime you cube a cube root, you're left with just that thing. So this is x plus 4 minus 4, which leaves me with just x. I've got to compose the other way, though, to check it. Sometimes it'll work one way and it won't work the other way, and those are not considered inverses. So g of x is equal to the cube root of something plus 4. And that something is f of x, x cubed minus 4. There's an understood 1 right here that gets distributed to get rid of those parentheses. So this is the cube root of x cubed minus 4 plus 4. Well, minus 4 plus 4 are opposites. So this is the cube root of x cubed. Anytime you take the cube root of something cubed, it's just that thing. So once again, we have an example of inverse functions. So in this case, g is also equal to f inverse. Yes, it is. Okay, whoops. Okay, so let's give a couple more a try. We're just trying to see if these are inverses of each other. So I'll start out with f of x equal to x cubed, and g of x equal to 1/3 x. So f composed with g is something cubed, and that something is g, which is 1/3 x. All right. So when I cube a fraction, I cube the numerator and cube the denominator. 1 cubed is 1. 3 cubed is 27. And then I also have to cube the x. 1/27 x cubed. I can't do any more simplification on this. And I did not end up with just x. So it really doesn't matter what g composed with f looks like, because I've already broken the rule for these things to be inverse functions of each other. So g is not equal to f inverse. And I don't even have to compose the other way to check that, because the first way I composed didn't even work. Okay. Last one for verifying if these are inverses. F of x equal to x minus 1 cubed, and my g of x equal to the cube root of x plus 1. So I'm going to start out with f of g of x. So that is something minus 1 cubed, and that something is g of x, and g of x is the cube root of x plus 1. Sorry, that cube root looks terrible. There's an understood 1 here that gets distributed to get rid of the parentheses. And I'm left with the cube root of x plus 1 minus 1 cubed. The plus 1 minus 1 are opposites, so this is just the cube root of x cubed, and the cube root of x cubed is x. Have to compose the other way to give it a check. So now we're going to do g of f of x, and g is the cube root of something plus 1 on the outside, and that something is f of x, which is x minus 1 cubed. Okay? There is an understood 1 here that gets multiplied by that cubic on the inside. So this is just the cube root of x minus 1 cubed, and then on the outside, plus 1. Okay, the cube root of anything cubed is just that thing. And so I have x minus 1, and then I have plus 1, which leaves me with x. So I have x here, compose f with g, or g with f, and I have x here, compose f with g. So in this case, g is equal to f inverse. Okay. All right, so looking into domain and range of functions. All right, the output of the function f are the inputs of f inverse. And we saw that in our first diagram where what we were putting into the machine on the inverse function was what we had gotten out. Excuse me, I've been up since 3 this morning getting ready for this lecture and the one immediately after this, so pardon the yawning. So the range of function f is also the domain of f inverse. Likewise, because the inputs of f are the outputs of f inverse, the domain of f is the range of f inverse. So that diagram is just a visualization of the fact that basically between a function and its inverse, you just flip-flop the domain and range. So if you have an f of x table that you've created for your function f, if you want to know what the f inverse of x table looks like, you just flip-flop your domain and your range. So your x and your f of x values. And we'll look at an example of this here in a moment. I did want to include this information about the square root of x because this is important here. When a function has no inverse function, it is possible to create a new function where that new function on a limited domain does have an inverse function. For example, f of x, that should say equaling, not minus, but equal square root of x, is the inverse function of x squared because squares and square roots undo each other. But if you remember back to our toolkit functions, the square root of x has a limited domain. So you have to limit your domain here when you are wanting to talk about these functions being inverses of each other. I also included this Q&A down at the bottom from your book. Is it possible for a function to have more than one inverse? And the answer is no. if two supposedly different functions, say g and h, both meet the definition of being inverses of one another, then you can prove that they equal each other. We have just seen that some functions only have inverses if we restrict the domain. In these cases, there may be more than one way to restrict the domain, leading to different inverses. However, if you're using the same domain, you're only going to have one unique inverse function. Okay, so that's just a general note saying that the domain of your function is the range of your inverse function and vice versa. The range of your function is the domain of your inverse function. So how do we figure these things out? So given a function, you can find the domain and range of its inverse. If the function is 1-to-1, write the range of the original function as the domain of the inverse and vice versa. Okay, so let's take a look at this. We have a function f, and we're told that the domain of f of x, actually let me move this down so I can have room to write the domain and range. So we have the domain of f as being x, and we have the range f of x. So this is just our function f. So we have 1, 2, 3, 4, and so on. And oh, I can't match these up. So there's an easier way to write this out. So let's say the domain of function f we are given is 1 through positive infinity, and the range of function f is negative infinity to negative 2, which 100% absolutely means that the domain of f inverse has to be the range from f, so negative infinity to negative 2, and the range of f inverse has to be the domain of f, so 1 through positive infinity. Now we can put we can use a table to show this next one. Okay, what we're told is for some particular function, f of x, we are given 2x values and 2 corresponding f of x values. So I have an x value of 2, and I'm getting that from this information right here. When I have an x value of 2, I have an f of x value of 4. When I have an x value of 5, I have an f of x value of 12. So if I want to know the domain and the range of my inverse function, I simply flip-flop my tables. 4, 2, 12, 5. So if you're ever given a graph of a function and you're asked to graph its inverse, all you have to do is create an f of x table for your function of key points, and then create an f inverse table by just flipping all those points, and then you can put it onto the graph quickly and easily. Okay, so suppose we want to find the inverse of a function represented in table form. Remember that the domain of a function is the range of the inverse function, and the range of the function is the domain of the inverse. So we need to interchange the domain and the range. Each row or column of inputs becomes the row or column of inputs for the inverse function, and vice versa. So we are given f of t here. And so for my inverse function, so this is the table for f of x, or f of t. And now I want to create the table for f inverse of t. So I still have t, and now I'm going to have f inverse of t. 1, 2, 3, 4. Okay, so t is going to be 20, 40, 60, 70. So for f inverse, these are going to be my p-values now. And then I have 30, 50, 70, 90 for f inverse of t. It's going to flip-flop for me. All right. Okay, so evaluating the inverse of a function given a graph. So this is what I was just talking about a moment ago. Given the graph of a function, evaluate its inverse at specific points. Find the desired input on the y-axis of a given graph. Read the inverse function's output. Okay, so their steps kind of make it sound confusing, and it's really not that bad. All right, so to graph an inverse function, what I do is on my function, and here I'm given my function g of x. I'm going to create a table of key points for g of x. I'd like 3, but I don't know if they've given us 3 good key points to focus in on. It looks like this function travels through the point 5, 3. It looks like it also hits 3, 1. And it looks like those are the only 2 good points for me to work with. So when I input 3, I get out 1. When I input 5, I get out 3. So if I want to consider my g of x, g inverse of x, all I have to do is flip-flop my table. That's the 0.13, and this is the 0.35. And I can put it onto my graph. So 1, 3, and 3, 5. Okay, so I know what this graph looks like, so I'm able to graph. And they didn't ask you to graph, but I think this is important for you to see. When you graph a function and its inverse, you will always end up with a graph that reflects over the identity line, the line y equals x. It will always reflect over that. That's a characteristic of inverses. Okay, so what they've actually asked us to do is use the graph to find g inverse of 1 and g inverse of 4. And it looks like we're going to have to estimate, I think. Well, not g inverse of 1. I think we're okay with g inverse of 1, but g inverse of 4 we're going to have to estimate. So let me continue this. And so let me put this point here. All right. So g inverse of 1. When I plug 1 in to the g inverse function, I get out 3. And that shows up right here, and it shows up in in g of x right there, 3, 1. I don't have, it looks like g function, when I plug 4 in, it looks like I get out about 1.75. So what that means is for G inverse, for me to, plug in 4, I know I'm going to be getting out 1.75 or thereabouts. So if I plug in 4 into the G function, this is not an inverse unless I have this function drawn incorrectly. No? Give me 2 seconds to think about this. So with the G function, that's my blue one, my original function. When I plug in 4, I get out about 1.75. Oh, I see what I've done. I was not thinking about when I get 4 out of the original function, because what I get out of the original function is what I plug into the other function. So, okay, so when do I get 4 out of the original function? That's what we need to figure out first. So I get 4 out of the original function. It looks like at about maybe 5.3, I don't know, 5.4. So in my original function, when I plug in about 5.4, I get out 4. So what that means is when I plug in 4 into the other function, I should get out about 5.4. So let's give that a check. When I plug 4 into my inverse function, I get out, well, you can see it's definitely more than 5. I'm off the graph. So G inverse of 4 is approximately, so I'll put a wavy equal sign, 5.4. Sorry for the confusion there for a moment. Okay, so this is where it gets real. How to actually find a function's inverse. If all you're given is an equation or a function, and you're asked what's the inverse of this function, we have a method of finding those. The first thing you want to do is make sure that your given function is one-to-one. Because if it's not one-to-one, then you have to start thinking about domain restrictions. Then what you're going to do is flip-flop, and actually I would say flip-flop these two, actually let me just give you new steps. 1, check for 1-to-1. The second step, since you know that the range of the function is the domain of the inverse function and vice versa, you want to flip your x and your y within, and in this case it's going to be my c and my f in your equation itself. And then if you've got x's and y's, then you're going to solve for y. So with this particular one, we have C and F. So we input our F value and get out our C value. So the inverse is going to be to input the C value and get out the F value. So we'll flip-flop and then we'll solve for F in this particular case to get its inverse function. Okay, so let's do that. We start out with C equals 5/9 F minus 32. And by the way, this is the equation to convert Fahrenheit to Celsius. So when we find its inverse, we're going to find the function to convert Celsius to Fahrenheit. Okay, so my first task is to flip-flop my variables. F equals 5/9 C minus 32. And I'm sorry, I'm actually solving for, let's see, so this is for X and Y. I'm actually solving for C here. Solve for C. No. That's just going to give us, yeah. Okay. So first of all, I want to get rid of this fraction by multiplying by its inverse, multiplicative inverse, which is 9/5. And I have to do that on both sides. So here's why I did that. 5 divides by 5, 9 divides by 9. So now I have 9/5 F equals C minus 32. Add 32 to both sides. And I get C is equal to 9/5 F plus 32. So what I have here is not C. What I actually have is C inverse. I used this to find it, but now that I found it, it's not C, this is C. C inverse is equal to 9/5 F plus 32, and C inverse is actually Fahrenheit. So we have a couple more of those to look at. All right, so we're given F of X. And F of X is equal to 2 over X plus 3 plus 4. And we're asked to find F inverse. So the first thing I'm going to do is write this with X's and Y's, just because it's a little bit easier to look at when you're thinking about solving for a particular variable instead of leaving the F of X in there. You can leave the F of X in there, but treat it as one unit itself. I'm going to rewrite it as Y equals 2 over X plus 3 plus 4. Okay, so my first task to finding the inverse is to flip-flop X and Y. So X equals 2 over Y plus 3 plus 4. And now I solve for y. So the first thing I'm going to do is subtract 4 off of each side. And I'm unpacking the box around y. Okay, so x minus 4 is equal to 2 over y plus 3. That y plus 3 is a unit right now. And so to get rid of that out of the denominator, I need to multiply both sides by a y plus 3. Y plus 3 comes out of the denominator there. So far I have y plus 3 times x minus 4 equals 2. So I'm going to get that entire factor of x minus 4 off of there. So I divide by x minus 4 on both sides, so it goes away there. Now all I have left on the left-hand side is y plus 3, and that equals 2 over x minus 4. I need to subtract 3 from both sides, and that'll have my y value isolated. So y, come up over here, y is equal to 2 over x minus 4 minus 3. Because that x minus 4 is an entire unit, so that minus 3 is out to the side. I really should compose these both ways just to verify that I've done it correctly. For the sake of time and for the sake of room on the board here, I'll skip that step. But once you have verified by composing both ways, you can then say that this is actually f inverse of x, 2 over x minus 4 minus 3. So that's how you do it. You flip-flop your x and your y, solve for y, rewrite as f inverse. Okay, so we've got another one to look at here. And we start out with f of x equal to 2 plus the square root of x minus 4. Now don't forget, we're going to have a restricted domain for this one. Oh, and actually there's a restricted domain for the first one as well. You can't plug in 3 to this first one, so you'd have a restricted domain on your inverse function as well. In this particular, this next one, you can't plug anything in less than 4, because if you do so, you're going to be creating imaginary numbers under the square root. So don't forget, when they start asking you about domain and range, be careful about that. They haven't asked us to do that in these two problems. They just want us to find it. But do note that both of these would have a restricted domain. Okay, so first thing I'm going to do is just change that f of x to y. So y equals 2 plus the square root of x minus 4. Okay, I'm going to flip-flop my x and my y, so x and y, and then solve for y. X equals 2 plus the square root of y minus 4. Okay, so I need to subtract 2 from both sides. And that gives me x minus 2 equals the square root of y minus 4. Square both sides to get rid of that square root. And that leaves me with x minus 2 squared equals y minus 4. And then I just need to add 4 to both sides to isolate the y variable. And we'll actually take a look at these two on the graph together. I think that'll be helpful to see. Okay, so I end up with y equals x minus 2 squared plus 4. So F inverse, and you would have a restricted domain, and I'll show you that restricted domain and how you can figure that out yourself once we look at the graph, plus 4. Okay, let's take a look. Let me just make sure that I'm on my business calculator before I share my desktop, and I'm not. Let me type it in. Okay, let me share my desktop and we'll take a look at these two. I need to write them down so I don't forget them once I leave the whiteboard. So we have f of x being 2 plus the square root of x minus 4, and our potential f inverse is equal to x minus 2 squared plus 4. Okay, let's go take a look. Okay, so I'm just going to put these two functions in. So f of x was 2 plus the square root of x minus 4. Okay, so notice the restricted domain. At an input of 4, remember I said you can't input anything below 4 because you're going to create imaginary numbers. So at an input of 4, anything less than that doesn't exist for this function. So the domain for this function would be 4 inclusive through positive infinity. And let's take a look at the inverse function. So that is x minus 2 squared and plus 4. Okay, so the output of 4 is where this thing is going to get restricted, because remember the domain of the first function is the range of the second function. So the domain of our inverse function can't go below 2. So we can't have any of these points here to the left. So really you should consider that stopping right at the vertex and not existing to the negative side through the domain. And you can also see if I graph the line y equals x, that is the line of identity. Look, if you cut the blue function off at its vertex, you can see that those functions reflect across the line y equals x. That is the identity line. Hopefully that was helpful for you. We'll go back to the whiteboard to finish up. Okay, so graph f of x equals x squared restricted to the domain. Find its inverse function and graph it on the same set of axes. All right, so f of x, we know this xy table very well. It's one of our very first toolkit functions. So we have x, f of x, and it asks us to restrict our domain from 0 through positive infinity. So 1, 2, and that's about all we're going to fit on this graph. So 0 squared is 0, 1 squared is 1, 2 squared is 4, and I will graph this function in blue. 0, 0, 1, 1, 2, 4. So this thing comes through, shoots up. All right, I need to find the inverse. So the first thing I'm going to do is replace x and y. So this is x equals y squared, and then I need to solve for y. So I need to take the square root of both sides. And in this case, y equals the square root of x. And I would say the positive and the negative square root of x, but it's not going to be the negative because of our restricted domain. But do remember you should take into consideration both the positive and the negative answers that come out. Okay, so my potential F inverse of x is the square root of x. And so the nice thing is I don't really have to do any work to create my F inverse of x table. I just flip-flop my F of x table. So 0, 0 flip-flopped is 0, 0. 1, 1 flip-flopped is 1, 1. 2, 4 flip-flopped is 4, 2. I'll graph this one in magenta. 0, 0. 1, 1. 4, 2. This goes like this. And if I came and graphed y equals x, it would go like this, cutting straight through as a mirror of reflection. Last page. Okay, same thing here, except we have a cubic to deal with this time. Okay, so we'll start out with f of x equal to x cubed minus 1. X and f of x. Okay, so let's get some negative values in there and some positive values. We do not have to restrict the domain because there are no restrictions on the cubic. So let's do negative 2, negative 1, 0, 1, and 2. Negative 2 cubed is negative 8. Negative 8 minus 1 is negative 9. Negative 1 cubed is negative 1. Negative 1 minus 1 is negative 2. 0 cubed is 0 minus 1 is negative 1. 1 cubed is 1 minus 1 is 0. And 2 cubed is 8 minus 1 is 7. So let's find the inverse function. So I'm going to flip-flop my x and my y. X equals y cubed. Take the cube root of both sides. Taking the cube root of something cubed leaves just that thing. So this is y equals the cube root of x. So F inverse is equal to the cube root of x. And let's make an F inverse table over here. The cube root of x. Oops, I forgot the minus 1. X cubed, let me redo that. Sorry about that. Once again, been up since 3 a.m. and it's 8 o'clock, so I've already gotten more than half of a work day in before 8 o'clock. Oh, goodness. All right, so x equals y cubed minus 1. So I need to add 1 to both sides first. Plus 1, plus 1. So this is x plus 1 equals y cubed, cube root of x. Sorry, cube root of y cubed. I want to take the cube root of both sides. And when I take the cube root of anything cubed, it leaves just that thing. So y equals the cube root of x plus 1. So I need to add a plus 1 to my inverse function up here. Okay, now I'm ready to create an XF inverse of x table. And just to prove to you that it works, flipping, that you really do get the true value, I'm going to work out my first input value. And I'm going to choose to input -9. So when I evaluate F inverse of -9, I get the cube root of -9 plus 1 is equal to the cube root, -9 plus 1 is -8. The cube root of -8 is -2, because -2 times -2 times -2 equals -8. So when I plugged in -9, I got out -2. Now look, it's the exact flip-flop of the function. So I can just go down and say, okay, I need to just flip-flop all my points. -2, -1, -1, 0, 0, 1, 7, 2. Okay, I'm going to put both of these on the graph, and this is our last slide, so we'll be done after this. -2, -9 is right here. I'm graphing f of x in blue. -1, -2, 0, -1, 1, 0, and 2, 7. So this thing comes through like this, and then it snakes across, and then goes up. Okay. And the inverse function, cube root of x plus 1, I have -9, -2, right here, -2, -1 here, -1, 0, 0, 1, and then 7, 2. So this thing goes like this. Notice if I graph the line y equals x, I get my line of reflection, my mirror. That's all I have for you on inverse functions. I hope this was helpful.